Hello everyone. Today, Ton, Tristan, and me, Vishnu, will be presenting our project analysis of student factors for dropout rates. Our team's goal with this project is to investigate what factors play a role in student dropout prediction, as well as can we utilize data mining techniques in order to predict potential student dropouts and allow early intervention to prevent it. Here's a quick outline. First, we're going to start with the introduction explaining why student dropout prediction is such an important problem. Then we'll talk about related work in the student dropout prediction space. Next, we'll walk through our approach and our application design. From there, we'll discuss our results, give a conclusion, and talk about future work. Finally, we'll end with a live demo of our application. First, for the introduction, dropout rates have significant impact on both students and institutions. From a student perspective, leaving school early can negatively affect one's career opportunities and long-term earnings, since not having a degree can limit students' career opportunities. For institutions, high dropout rates can reduce the number of students who attend. It can also reduce funding, student retention overall, and overall student performance. Because of this, being able to predict which students are at risk of dropping out is extremely valuable. In this project, we apply several data mining algorithms, logistic regression, decision trees, and naive Bayes to create predictive models. These models can be deployed to help institutions intervene early and support student success. So first, when talking about work related to ours in previous papers, when reviewing related research in this field, we found several papers examining the subject. Past studies show that institutional intervention, like advising, mentoring, and academic support, is one of the most important intervention factors for preventing student dropouts. Prior research has also identified important features such as GPA and gender and their effect on student dropout rates. At the same time, machine learning methods like support vector machines, random forest, and ensemble approaches have been used with promising results in previous research. These studies help motivate our decision to compare multiple algorithms and evaluate which ones perform best on our dataset. Our research focuses on using a complex dataset with over 30 features to identify the most important, as well as we utilize 3 different data mining techniques, which we think will be able to provide accurate insights. For our proposed work, our proposed solution is to develop an application that allows institutions to input student information directly, and they can instantly receive a dropout prediction. To make this possible, we use a feature-rich dataset that captures many aspects of a student's background and academic history. This allows us to build informed models and also visualize the data in meaningful ways. The goal is not just to classify students, but also to provide insights to allow institutions to be able to act on, to prevent student dropouts in the future. For our dataset is actually from the Polytechnic Institute of Porto Alegre, which is in Portugal. It's also from 2021. In this dataset, there are 4,424 records. Each of those records represents a student, and each of those records has 36 attributes. Those 36 attributes are each a feature which represent information about the student, such as their GPA or past academic history. With our dataset, we use post-pre-processing in order to remove irrelevant features and to be able to transform the data into a binary classification problem. Our dataset for our actual work is condensed into 21 attributes from those original 36, where 6 are numeric and 15 end up being categorical.
So for our proposed work, our application, we wanted to build a really simple application that had a simple and minimalistic UI design. Additionally, we wanted to build all the features to be very intuitive, have the interactions and visuals that the users would actually want to use, as well as it being really practical in terms of, for professors or any type of academic advisor. So for our application, the primary tools that we used for this was Python. We essentially use libraries from Python such as pandas and matplotlib and numpy to do any form of calculations and plotting. And then for our overall web framework itself, we actually use Shiny. Shiny offers a Python implementation that which provides us ways to create reactive interactions that will update in real time. And this makes it really easy to spin up an application and also to essentially plot everything that we need, as well as its overall integration with, as I mentioned, like matplotlib, for example. So to start, the figure on the left here sort of shows our initial ideas of our sketch that we had of what our application looked like. The sketch was kind of very bare in the sense that we wanted to know, what do we want on our application? What do we want our users to see? In this case, we knew that we wanted sort of 4 primary things, right? The first is we wanted some type of way to take an input. The second is the result of those inputs, so the classification results. Third, maybe a data preview, and actually we also wanted as well as a visualization, right? So some way of visualizing the actual performance of the 3 methods we had and provide a little bit of justification on why we picked 2 out of the 3. On the right is sort of that sketch implemented in Figma. We wanted to see, for ourselves what that might look like, and this is sort of just a simple representation. During the time of this development, we didn't really have like the actual classification results, nor did we have like the visualizations solidified yet. So we sort of made a guess of what those might look like, and this kind of gives you a rough idea of what it possibly could be. Now, with that being said, as we slowly began to build the application, what we did notice is that the number of features that we will actually have for the inputs that the users need is a lot more than just these shown here. And as a result, we thought it might be better to start actually sectioning these pages off into specific sections, right? So like, for example, the prediction stuff will be on one page, and then maybe the visualizations will be on one page, and then the data preview will be on another page. And then this next 4 figures here sort of displays that, right? So, I won't go too in depth into this, as we'll go a lot more in depth when we look at the demo. But starting at the very top here at the proposed work, for our proposed work application here, we have the analysis showing a data preview of all their data sets. Then on the top right, we have the classification prediction tab where all the features are on the left here, and then you can choose whichever method you want. The bottom left is one of the other functionalities that we decided to do, which allows users to do a mass prediction where they can upload their own CSV files and then predict on all those rows simultaneously. And then the last figure is where the visualizations we mentioned, which kind of shows the justifications on why we pick specific methods over the other for our final product.
Moving into the different algorithms we chose to implement for this application, we chose 3 different classification models to implement. The first of which is decision trees, second is naive Bayes, and the third is logistic regression. And we'll get into the details of each of these and why we picked them. So decision trees, at a high level, they basically are a tree-like structure that partitions the instance space. So as you can see in the image, the nodes actually represent the attributes of your data set, and all the edges represent the values for the specific attribute. The leaves represent the labels of each instance, or just represent labels. And the decision trees use an impurity measure, which is basically just the uncertainty or mixture of class labels of your data set to determine what attribute to split on and where to split it. So looking at the image here, you can see the root node is windy, with the edges being true or false to indicate that it is a binary attribute. And then for numerical attributes such as temperature, instead of enumerating an edge for each possible numerical value, you have a threshold. In this instance, it's 83, where it kind of splits the data set into temperature values that are less than 83 or greater than 83. And this does not, this structure is not limited to binary categorical attributes. It is also applicable to attributes with multiple categories. So as you can see, the outlook can either be sunny, overcast, or rainy. That's 3 edges, and then they lead into either humidity and then either yes or no for the labels.
Now moving over to naive Bayes. So the primary thing about these naive Bayes algorithms is that they're based off of Bayesian decision theory. So when we think of Bayesian statistics, one of the most well-known one is the Bayes rule, and this algorithm sort of plays within that, except that instead of instead of finding the probability of trying to find the probability of a class given that you have a set of features, it's sort of more inverted, right? In this case, you're more if we have the labels in this case, given that we know the label, what is the probability of these features occurring is sort of the shift in focus for naive Bayes. Some of the important aspects of it is that it makes some assumptions. So for starters, it makes the assumption that all the features are independent of each other, or in other words, meaning that sort of the ordering of these features don't matter, or whether or not they exist or don't exist doesn't really matter in this context. And a largely part of that is that it enables for faster calculations, right? So if you had to do a conventional Bayes rule, what you'll find is that you might have to worry about the specific ordering, whichever one, if there's any dependencies between your features. And in our case, most of our features have independence between one another, meaning that this algorithm will be a lot more suitable for us. Additionally, when we think about naive Bayes, there's also definitely a bias when it comes to specifically categorical data, which is what naive Bayes primarily focuses on and does really well with. So as a result, we decided to also include a subvariant of naive Bayes, which is the Gaussian naive Bayes. And all that is simply assuming that any feature that is continuous utilizes or follows under a Gaussian distribution. So for our implementation, we have a naive Bayes that is for categorical data, and then we'll switch over to Gaussian naive Bayes when it comes to continuous data. This allows us to be a little bit more robust when it comes to the data so that we're not assuming that all data sets are categorical, for example. So just to look a little bit more into some of the equations here, right? So when we look at the naive Bayes equation, we're essentially trying to figure out, based off of this prior right here given the prior of a class multiplied by the sum of products, given that we have that class, what is the probability of it having this specific feature, right? And it's going to essentially pick the class that is most likely to be the case to have these features. And that's essentially what the focus here. And on the right just shows you a modified version of that probability here, where it utilizes sort of that Gaussian form there to account for those continuous factors.
So for our algorithms, we also chose to implement logistic regression. Logistic regression is a classification algorithm where we predict a binary result. In this case, we want to predict if a student will drop out or not. And this is very similar and uses many techniques of linear regression, which is not a classification algorithm. But they use many of the similar techniques, including assigning weights and biases to each feature in order to predict the value. As well, it also utilizes a gradient descent algorithm in order to update the weights and biases based on the algorithm's accuracy to better fit the data in future rounds. Logistic regression utilizes a sigmoid function, which is different from linear regression, in order to change the probability to a binary result. The model utilizes a gradient descent algorithm to adjust the weight and biases after each training round, which also allows the most important features to get more weight. But one potential downside of logistic regression is that it might not be able to effectively find some of the underlying complex patterns that other machine learning techniques may be able to use, such as neural networks.
Now we're going to get into some of the different ways we're going to test the performance of our models. And the first of our evaluation metrics is going to be our confusion matrix. This just displays the true positives, true negatives, and false negatives of our model. And this 2x2 matrix is basically a simple, compact way of summarizing how each model performs, and then provides a nice visual for kind of displaying each of these numbers. And an important fact about the confusion matrix is that if you sum the entries in the main diagonal, that signifies all the correct classifications, and then the sum of all entries in the matrix. In this particular instance, since it's a binary classification problem, it's going to be 2x2, so just the sum of all 4 entries. That'll give us the total number of points in the data set that we tested on. So dividing the sum of the main diagonal entries by the total sum is going to give us the accuracy that each model achieved. Second of all, we chose to evaluate our models using precision recall curve. This plots the precision versus recall for different probability thresholds. Precision being out of all positive predictions, how many of these did we get right? So this is based off of what our model guesses. The recall is out of all actual positive cases, so the ground truth, how many did we predict correctly? In both instances, the precision and recall focus on the positive class, so this kind of evaluates how our model is detecting these positive classes, or these positive cases. And in this particular instance, since our data set is more imbalanced towards the non-dropout, since dropout is kind of a naturally uncommon occurrence among students, we want to have more importance on the positive cases and predict whether or not a student is actually going to drop out, since that is what's more important to detect. And then the last metric we have is the receiver operator characteristic curve. This plots the true positive rate versus false positive rate for different probability thresholds. And this is just going to be a general performance metric that is independent of the class imbalance. The reason being is because since they are true positive rates and false positive rates, the rates kind of scale to how many attributes are in the data set regardless of the percentage of each. Since they are a ratio and not a raw count of positives or negatives, if you have 10 times the number of negative instances than positive cases, the ratio will take care of that imbalance in proportion. And for both the precision recall curve and the receiver operator characteristic curve, what's important is the area that is accumulated under each of these curves. A higher area in both curves means that the model is more performant and thus better. Moving on to the actual results we received, this is just at the top showing us each confusion matrix for each of the models. A couple things to note. When we look at the logistic regression confusion matrix, for instance, the column that relates to the dropouts, so this kind of light green, almost white column here, this is the predicted label section, and this is when they predicted dropouts. And you'll notice that it's 11 and 6 out of almost 1,300 instances, which basically means that logistic regression almost exclusively is biased towards predicting non-dropouts. Decision trees and naive Bayes, however, have a more clean spread of dropouts versus non-dropouts. As you can see, the column sums for predicted dropouts for both of these models are more or less proportion to how much the dropouts take in the actual data set. So if you sum up the main diagonal entries for decision trees and naive Bayes, and then divide it out by the total sum, you'll come to find that they have almost identical accuracy scale or accuracy scores, with naive Bayes narrowly beating out decision trees. Decision trees, if you calculate the accuracy score, would come out to around 76% accurate, while naive Bayes comes out to around 77% accurate. So naive Bayes has a slight edge over decision trees, but both models are fairly accurate in terms of just raw number or proportion of correct predictions. Moving on to the bottom left, we have the precision recall curve for each model. As you can see from the legend in the graph, the blue curve corresponding to logistic regression is a lot lower and thus accumulates less area than the other two. And then the natural progression from the rest of the models down the legend corresponds to which ones perform better in terms of precision recall. From the graph, you can see that the green curve is above the orange curve, meaning that naive Bayes is accumulating more area in the precision recall curve than the decision tree curve, which means that naive Bayes wins out cleanly over the other two models in this metric. And then lastly, the receiver operator characteristic curve, the ROC curve on the bottom right, you can see that decision trees and naive Bayes are much closer in this aspect, while logistic regression tended to fall behind with a much lower area under the curve score. And this, combined with the information from the precision recall curve, means that naive Bayes was more accurate in detecting the positive cases, which is important in our context because we want to be detecting whether or not someone is actually at risk of dropping out. So naive Bayes outperformed decision trees and logistic regression in this aspect. However, decision trees in the ROC curve is almost identical to the naive Bayes curve, meaning that overall it was almost as accurate as naive Bayes, except its predictive power for the positive cases is lower. So for our particular application, decision trees is slightly less preferable to naive Bayes, but overall their performances beat out logistic regression in all metrics that we measured. So we chose to integrate decision trees and naive Bayes into our application. So to wrap up, the student dropout is a major concern that can impact one's education and future career prospects. And we try to combat this issue by constructing different classification models to detect students at risk of dropping out, and then integrate them into an interactive application to where educational instructors and administrators alike can kind of predetermine which students are at a higher risk of these dropouts, and hopefully take preventative and proactive measures against this. Decision trees and naive Bayes, out of the 3 algorithms we chose, were found to be the best performing algorithms in our application, as they outperformed logistic regression, our third model, in every performance metric.
And then finally, when we look at sort of what the future holds for our work, I think there were 2 primary things that we sort of considered doing as well, given that if we have more time. The first would be identifying which feature is most significant in contributing to a specific class that is not academic related, right? So as we mentioned earlier on with related work, a lot of the research is focused on a lot of things about academic factors, right? Things such as GPA, the courses they're taking, how many credits have they accumulated. We're also interested in looking at other factors. Maybe what exactly is the world looking like at the time? What is the GPA looking at the time? What is the employment? Do people feel unease to go to college because maybe employment is really difficult and they want to get a job now, right? Those are some of the features that we think could have a significant contribution to dropout, and I think being able to identify those would be really important. The second one would be training models given input in real time. So in other words, users are able to provide their own training data, and then we'll have our logistic regression rebuild its model, or our decision trees rebuild the trees and everything, and just have it all build in real time for the user instead of having to rely constantly on our model. I think that's just a really neat feature to have. Obviously, not very practical if we had machine learning methods. However, in our case, I think it still is definitely something that could be considered for a application purpose. With all that being said, here's the references that we used in our presentation. For our references, we do have more in our paper. You can just refer to the actual paper. It will have all 10, but for our presentation, we kind of just hit on some key ones that we thought should be brought up. All right, so for our demo here, we will go onto our locally host Shiny app here. So right away, as we mentioned earlier, we have sort of a data preview page. This data preview page here will show you essentially a preview of our data in regards to what exactly these targets look like. So for example, how many dropouts do we have? How many non-dropouts do we have? Tell you the number of records, number of features. In this case, we have 20 instead of 21 because one of them, as you can see in the far right from this table here, one of them is actually the target. So we only have 20 features that we'll be training off of. Then moving on to the second tab is the prediction and classification. So for this tab here, the user is able to do multiple inputs based off of all the 20 features we have. And they can also decide between which method, and then when they're ready, they can hit the predict button. So as you can see here, there's different options you can pick between your user's record of what they want to input. And then when you're ready, you hit the little predict button here. And then whenever it's ready, it'll predict whether it's a dropout or a non-dropout. As we mentioned earlier, one of the other functionalities we realized is that filling out 20 of these fields here is a lot, right? It's kind of difficult to actually fill this out. So as a result, We also provide users the options to do a mass input where they can upload a CSV of multiple records. So we can go through here real quick, and then when we go over to our mass data that we've prepared, and then let's just use naive Bayes for this one. We hit the little mass prediction and classification button, and then it'll drop down the table of their CSV file that they have. And then at the very end of their CSV file, we'll also append the classification result. So some of them here you notice are dropouts, some of them are non-dropout predictions. And then our last functionality that we thought would be really nice is being able to export this as a CSV, allowing them to essentially use it for whatever needs they may have. And we also timestamp it just to give an idea of when they save this so they don't make any duplicate saves. And the last and final page that you saw from our results and our analysis is the visualization page. This shows users sort of a quick preview of the methods that we compared and justification on why we decided to go with decision tree and naive Bayes.